Hi, today we're going to be looking at how we can take a look at different integrals if we were to combine something like a transcendental function and an algebraic function. Now you may recall from your previous math class that a transcendental function is anything that cannot be written as a power, like e to the x, sine of x, natural log of x, or an algebraic function is something like 1 over x, x cubed, and like 4x, where I can write them as a power. What we're going to take a look at today is, well, what happens if we want to integrate something like this? If I were to combine the two, something like x cubed times e to the x dx. Now notice, that's a lot different than if I write it this way. If I had x cubed times e to the x to the fourth dx. In a case like this, in a case like our second example, we can use substitution, because our derivative would be 4x cubed dx, and those will cancel. However, like in our first one, use substitution will not work, so it fails. So we have to come up with another technique. And that's what we're going to talk about today. And our technique we're going to use is what we call integration by parts. Integration by parts is how we integrate functions if we have an algebraic function and a transcendental together. Now later on, we're going to answer the question: what happens if we have two transcendentals? I can't spell that today. Transcendentals. There we go. Why I majored in mathematics. So we're going to take a look at what happens if we have two of them. Now there's a rule for us. So let's go back to a kind of a simple example. Let's say we have the function x times e to the x dx, and I want to integrate this. Use substitution clearly won't work. So what we're going to use our rule for today. And here's the rule for integration by parts. It's going to be this. It's going to be u dv equals, now we're going to talk about what these mean in just a second, equals equals u times v minus the antiderivative of v du. This is our rule. This is what we call integration by parts. What that basically means is we're going to take these two functions and we're going to split them into two different parts. One of them will be a u and the other one will be a derivative, or dv. It doesn't really matter which one we pick for which. We'll explain that more in just a few moments. But to get started with, let's go ahead and for this example, we're going to let x be u. Or I should write that the other way around. U equals x. Which means this e to the x dx is my dv. It's e to the x dx. Now this is kind of tricky the first few times we use it. Now, what I'm going to do here is I'm going to use my rule here. So I let one be u, the other be dv. Well, I need to find v. Well, to find v, for this one, I'm going to take the antiderivative. So the antiderivative e to the x is just e to the x. Now notice I also need du, and that comes from here. In other words, I'm going to take the derivative of this one. And I get du equals dx. And I just plug it into my rule. Well, my rule says to just take u, multiply it by v, subtract out the antiderivative v, du. And I just plug them in. I get x times e to the x, so x e to the x, minus the antiderivative of e to the x, v du, dx. And if you notice, what happens here is it gets a little bit simpler for us, x e to the x. So we get x e to the x minus the antiderivative e to the x, just e to the x plus c1. And there's our final answer right here. Like I said, this does take a little bit of practice for the first few times. So let's take a look at another example here, kind of the same type. What if we do the antiderivative of, let's say we have x times the sine of x dx. Again, I have a transcendental function multiplied by an algebraic function. So my rule says my rule says this is going to be an integration by parts. And the rule says this one is going to be u, the other one's going to be dv. I just have to pick which one. Now, here's my hint. This is the hint. I'm going to drop a hint for you. Most of the time, now there's one exception, most of the time, u is the algebraic function. And the reason we say u is the algebraic function is because if I continue taking the derivative, which we'll see in the next example, it goes away eventually. So I'm going to let u equal x, there's my u, and this is my dv. So my dv is the sine of x dx. I need this uv minus the antiderivative of v du. So we get du equals dx, nice, and v, I take the antiderivative and I get negative cosine of x. And I just plug it in. We get u times v, so negative x cosine of x minus the antiderivative of v du. So that's negative. If I factor out the negative, that becomes a positive cosine of x dx. And if you notice, if you choose the right u, it'll go away inside the second integral right over here. So we get negative x cosine of x, and what's the antiderivative of cosine? Sine. So we get plus sine of x plus c1. And there's our antiderivative here. So let's take a look at a slightly more complicated one. Okay? What happens if I do something like x squared? Let's times this by e to the x dx. Now, the same thing. My rule is this. Because u substitution won't work, so I use my integration by parts. That's going to be u, and that's going to be our dv. So I'm going to write over here, u equals x squared, dv equals e to the x, du is 2x dx, and v equals, boring, e to the x. But watch what happens this time when we plug it in. Let me focus here real quickly. But watch what happens when we plug it in. I'm going to get u times v, so I get x squared e to the x minus the antiderivative of v times du. And I'm going to manipulate this a little bit. I get 2x e to the x dx. Now, notice the difference. Here versus up here, cosine of x just became sine. But here, I have another integration by parts. So I have to do the same process again. So I'm going to let u equal 2x, my dv equal e to the x. So du, 2 dx, v is still e to the x. And I do it all over again. I'm going to get x squared e to the x minus, I'm going to put a bracket here because this is another integration by parts, u times v. So I get 2x e to the x minus the antiderivative of v du. So I get 2 e to the x dx. And if you notice, again, if you choose the right u, the power is going to go down. We went from x squared to just x to just 2. And from here, we can actually get the answer. We're going to get x squared e to the x minus 2x e to the x. Be careful. Plus 2, that just becomes e to the x plus c1. So far, so good. Not bad, right? So far, these are pretty good. I mean, they're not hard to do. So before we take a look at a couple hard ones here, let's take a look at how we integrate natural log. So, and then we'll go to part 2, okay? What if we want to take the antiderivative of the natural log of x dx? Now, we've never done this before. We know the derivative is 1 over x, but we don't know the antiderivative of natural log of x. So to solve a problem like this one is, we have to use integration by parts. So the question is, what's going to be u? What's going to be dv? Well, if I let's just say we let natural log equal dv. It would be natural log dv. To find v, I would have to integrate. Well, we already don't know that because that's what we're trying to do anyways. So I'm not going to let natural log be dv, I'm going to let natural log be the u because I do know its derivative. And what's the dv going to be? Whatever's left, just that dx. There's our u, there's our dv. Take the antiderivative, take the derivative, du, we get 1 over x, dx, v is just x. I plug it in. My rule, u times v, x, natural log of x, minus the antiderivative of v du, x times 1 over x dx. And very nicely, those just cancel. We get x, natural log of x, minus, that just becomes x, plus c1. And there's our antiderivative. If you go to part 2, we're going to take a look at a few more examples here, a little bit more challenging ones, so I'll see you then.